When we talk about dissolves, the first thing that comes to mind is polarity. The more similar, the better one substance dissolve in another. Polarity comes from the existence of a dipole moment, the distance between positive and negative charges. Polar molecules usually have a permanent dipole moment, while nonpolar molecules can also develop an induced dipole moment under the influence of the electric field of a polar molecule. However, for substances with higher polarity, hydrogen bonding also comes into play. Since the strength of a hydrogen bond is greater than that of a dipole-dipole interaction, it adds another layer of complexity to understanding why dissolves. Let's exclude the influence of hydrogen bonding for now. Then what we first need to understand is how dipole-dipole interactions arise. When two polar molecules come close to each other and their dipole moments are similar, their dipoles interact to create electrostatic attraction. The positive charge center of one molecule is drawn to the negative charge center of another. Interaction causes polar molecules to align in a way that minimizes their potential energy, with the positive and negative ends facing each other. If the dipole moments are not similar, then while one end of the molecules may attract each other, the other end won't align. As a result, the overall energy cannot be minimized. Since the two substances fail to achieve an optimal molecular arrangement, they do not dissolve well in each other. We can understand this through the energy changes involved in the dissolution process, which includes three main components. 1. Solvent-solvent interaction energy, delta H1, the interaction energy between solvent molecules. 2. Solute-solute interaction energy, delta H2, the interaction energy between solute molecules. 3. Solvent-solute interaction energy, delta H3, the interaction energy between solvent and solute molecules. The total energy change during dissolution can be expressed as delta H equals delta H3 minus the sum of delta H1 and delta H2. When two polar substances with similar polarity mix, they have an energetic advantage. In this case, delta H3 is usually large, while delta H1 and delta H2 are relatively small. And since delta H3 is close in magnitude to delta H1 plus delta H2, the overall delta H becomes small. That is, the total energy change is small, meaning the dissolution process occurs more easily. This happens because molecules with similar polarity form stronger dipole-dipole interactions, effectively lowering the total energy of the system. In addition, the entropy effect and mixing free energy also play a crucial role. Whether the dissolution process occurs spontaneously depends on the change in Gibbs free energy. According to the Gibbs equation, delta G equals delta H minus T times delta S, where delta H is the enthalpy change, T the temperature, and delta S the entropy change. We further explain this phenomenon. Solvents with similar polarity feature a clear entropy advantage. When the solute and solvent have similar polarity, delta H tends to be small, while delta S is large. This happens because mixing similar polar molecules significantly increases the disorder of the system, resulting in a higher entropy value. As a result, the change in free energy becomes negative, meaning the dissolution process occurs spontaneously. For polar compounds, even without considering hydrogen bonding, the principle of dissolves can be summarized in three key points. First, stronger dipole-dipole interactions form between molecules of similar polarity, resulting in a more stable solution. Second, when the solvent and solute have similar polarity, their interaction energy is higher and the overall enthalpy change is smaller, making the dissolution process energetically favorable. Last, mixing molecules with similar polarity increases the disorder or entropy of the system, thereby reducing the free energy and making dissolution occur more easily. To truly understand why substances with similar polarity dissolve in each other, we must grasp these fundamental principles and then continually test and verify them through practical applications such as solvent selection, derivatization reactions, and chromatographic separation. By doing so, we gain the ability to look at the field of chromatography from a fresh and more insightful perspective.